Welcome to the next lecture in the course CHM 221, Basics of Physical Chemistry. In the previous week of lectures, we saw the phenomenon of electrolysis. We got introduced to basic terms that are present. We also took a brief look at the history that went into characterizing these kind of phenomenon. And most importantly, we were also able to put forth the quantitation of such processes in terms of the Faraday's law. In this week of lectures, we will be carrying forward and trying to understand this phenomenon of converting electrical energy into chemical energy, but in perspective of conductance of given electrolyte which you are employing. Once again, as we did in the previous lecture, we will be defining some basic terms starting from very fundamental units that we are already aware of, and then try to picture a little bit of how does the experimental setup work out such that one can reliably measure various parameters that are going to help us understand the phenomenon of electrolysis further. Most importantly, the measurements that end up resulting in data would also be analyzed in order to understand how things work out. I would continue lecturing by following the textbook An Introduction to Electrochemistry written by Samuel Glasstone. And we have graduated ourselves to the second chapter of this textbook, which is called Electrolytic Conductance. I strongly encourage all students to go take a look at this book so as to follow the lectures in a coherent fashion. In order to understand what is conductance, the first thing that we need to familiarize ourselves with is resistance, more particularly specific resistance. Let's try to recollect some aspects that we might have learned already in either this course or previous course. We are well aware of the fact that when you have a conductor which can transmit current, it is associated with a certain resistance that's present. And we define this resistance as the inhibition offered against the flow of electrons. And if you might remember, the resistance is related to the EMF applied in the current by the Ohm's law. While we are aware of it, we will try to define what is resistivity. In order to do this, we will be mapping or approximating this current carrying conductor into something like a cuboid. From this cuboid, we will be trying to understand how one can determine what is the resistance of this entire coil. And for this purpose, we are going to divide this current coiling conductor into multiple cuboids, and each of this cuboid is composed of even smaller cubes, each of which are 1 centimeter cube. And the area that is occupied by this given square is going to be a centimeter square, and the length of this conductor is going to be assumed as L centimeters. So let's try to draw this part of the cube. What do I mean by this is that each one is associated with a 1 centimeter cube. Of course, I'm not drawing it in 3 dimensions, but you're able to realize that is a slice of this entire conductor that we are talking about. The resistance offered by this small 1 centimeter cube unit is called the resistivity, which is given the symbol rho. You might remember from your previous classes or courses that when you have two resistors that are connected serially, then the total resistance offered by this conductor will be the sum of resistances 1 and 2, R1 and R2. On the other hand, if you have two resistances that are connected in parallel, then the reciprocal of the total resistance is going to be given by the sum of reciprocal of individual resistances. That is 1 over R is going to be equal to 1 over R1 plus 1 over R2. When you're taking a look at this as a conductor, you're having many such resistances that are set to each other, and they are in parallel fashion, largely because if an electron does enter here, it could actually flow into any of these cubes in not any particular fashion, definitely not in serial fashion. So basically, this can be imagined as a set of parallel resistors that are present. Just for the sake of simplicity, if small r is the resistance offered by this single unit, then it's going to be sum of 1 over rho up to a times. And this comes up because you have a centimeter square as the surface area, and the length of each one of the sides is 1 centimeter. So there are going to be a units of this 1 centimeter cube in order to make up this 1 unit. So this is going to be equal to a over rho. Therefore, the resistance of the small unit is going to be rho over a. Now followed by that, if you are going to have multiple of these segments that are added up together to get the entire conductor, what is going to happen is that resistance is going to be rho over A summed L number of times, because you remember the length of this is still 1 centimeter and the total length of the conductor is L centimeter. So the resistance is going to be given by rho times L over A, where rho is the resistivity or specific resistance for the conductor that you're looking at, and R is the resistance present in ohm, L is going to be in centimeters, A is going to be in centimeter square, implies rho has the unit ohm centimeter. That is, specific resistance or resistivity has the units ohm centimeter. So now that we have understood what is resistance, conductivity C is nothing but 1 over resistance. It is obvious sense that if you are having larger resistance, then the conductivity is going to be less, meaning that the flow of electrons would be low, and hence conductivity or conductance and resistance have an inverse relationship with respect to one another. So let's continue to write. R is going to be given by rho L by A, and C is equal to 1 over R. So therefore this is going to be equal to 1 over rho times A by L. This 1 over rho is a quantity called kappa, which is the specific conductance or conductivity. Old textbooks might call it specific conductance and newer textbooks call them conductivity. And in the same fashion, what you are able to realize is that what are the units of each one of this? Conductance has the unit of ohm inverse, which is also called Siemens. And you have area, which is going to be centimeter square, and length is going to be centimeter. So therefore, the unit of kappa is going to be equal to Siemens per centimeter. Some people also call it per ohm per centimeter or mho centimeter inverse. Mho is nothing but inverse ohm, but these are not commonly used. The SI unit will be Siemens, centimeter inverse. Okay, now having said this, we'll try to define what is conductance. Let's assume that for a centimeter cube, A and L are going to be 1 centimeter square and 1 centimeter respectively. And then if you're applying an EMF of 1 volt, then what ends up happening? You have E equal to IR, which is going to be I over C. And if you're going to set it to 1 volt, what ends up happening here is that you have 1 volt equal to I by C. And you remember C is kappa times A by L. If A is 1, L is 1, then C equal to kappa. Then this means that the current that flows is actually the conductivity of this system. So this is basically how it is defined for a given conductor. Since we are associating ourselves with electrolytes, the term that has more prominence is actually equivalent conductance. So let me write whatever we got earlier. C is kappa times A by L. This is what we got introduced to a moment earlier. Now the specific conductance is defined as the conducting power of all ions produced by one equivalent of electrolyte in a given solution at a given temperature. So imagine that you have two parallel electrodes that are set 1 centimeter apart of each other. And then let's assume that you are able to put one equivalent of the electrolyte that you are trying to assess in this solution. And let's assume that the volume is V centimeter cube. So the volume is V centimeter cube and you have 1 centimeter as the separation, then you immediately understand the area is going to be V centimeter square that is interacting for the electrolyte to that of the solution. So therefore what ends up happening is that you're going to have the conductance, the equivalent conductance written as capital lambda will be equal to kappa times V, that is in the volume, the area divided by 1 centimeter. That's what ends up coming here. But remember one thing, we are talking about equivalence in 1 liter. Okay, so just to quickly give you a definition of equivalence in a liter, I'm sure you might remember from your school, normality is defined as the number of equivalents divided by volume of solution in liters. But currently, we are defining volume in centimeter cube. So therefore, if you're just going to be converting centimeter cube into, which is ml, into liters, there's going to be 1,000 factor that comes in. So therefore, equivalent conductance is going to be given by kappa times 1,000 by C, where C is the concentration in equivalents per liter. Okay, so basically this is the normality that you are trying to estimate or determine the concentration in, while the equivalent conductance is what you're trying to measure for the electrolyte with the specific conductance or conductivity of this electrolyte given as kappa. So this is an important relation that we are going to be looking at time and again. And once we end up measuring lambda for different electrolytes, we are going to understand what is the effect of concentration that ends up coming. As you are able to see, this is of an equation which is given by something like y is equal to m divided by x, where x is the variable and y is the dependent parameter that ends up coming. So if you end up plotting such functions, you end up getting dependence as a function of x. So I'm just plotting x, and this is y. I'm plotting y equal to 1 over x in blue, 2 over x in purple, and 3 over x in a different shade of brown. So this is 1 over x, and the middle curve is 2 over x. And what you're able to see is that as the constant keeps increasing, the curves start going away from each other. So this is the same kind of equation you're trying to look at, kappa times 1,000 over c. However, in the plot that I've done, the constant number actually ensures such a dependence, but in the measurements that we are trying to do as a function of concentration, kappa doesn't have to remain a constant, and this is what we will end up measuring. And the way we would end up measuring is what has just been shown, is that if you are able to get an electrode such that, or rather, if you're able to get a device such that the electrodes are 1 centimeter apart from one another, and if you're able to put a certain concentration of the electrolyte that you're trying to see between these electrodes, then the current that you end up measuring would be the specific conductance that is going to be present. Once you get the specific conductance, you should be able to get what is the equivalent conductance that is present. So before going ahead to looking at the results, let's try to take a look at what considerations are required. First of all, you will have to be making an aqueous solution of the electrolyte, and while you're trying to prepare an aqueous solution, you need water as a solvent. Crucially enough, distilled water is a very poor conductor of electricity. However, the impurities that could potentially be present in water could cause trouble. And I mean impurities, we are talking about dissolved carbon dioxide or ammonia or even the dust particles that might be present. And this would end up becoming a menace for measurements which involves dilute solutions or weak electrolytes, largely because when you have very dilute solutions, the number of ions that would be responsible for conductance is very small. Now, if the impurities are present, which might end up interfering with such a measurement, might start conducting themselves and would create problems. So therefore, the need for the solvent to be pure is of imminent importance. And also, if the conductance, if we're just a linear sum with respect to the solvent, meaning that, let's say you're trying to measure the total conductance that comes up, which is just the sum of the solvent and that of the electrolyte. So for instance, we are talking about, let's say, KCl as the electrolyte. If it is just a basic sum of the solvent and that of the electrolyte, and the solvent conductance doesn't change, one can just measure this for the pure solvent, and for every measurement that you end up doing, it's just basic correction that ends up coming. However, this is not always the case that things might end up working. Sometimes the impurities might start influencing with the ionization of the electrolytes. So for instance, just as an example I'm giving, let's say there is an impurity of NaCl, which is going to be present as Na plus and Cl minus ion. And if you're trying to do your measurements with KCl, which will also dissociate as K plus and Cl minus, the problem that will end up coming here is that due to the common ion effect, which means that if you have the same ion that's going to be present, it's going to end up favoring the backward reaction, in which case KCl is not going to be completely dissociated. So due to this, what will end up happening is that you might not end up measuring the pure conductance of KCl in the presence of NaCl as impurity that causes erroneous measurements. Or on the other hand, what could potentially happen is that the impurity might end up causing a chemical reaction. For instance, if you have sodium chloride as the impurity, and if you're trying to use silver nitrate as the electrolyte, what will end up happening is that you will form AgCl, which will end up precipitating, and therefore you're not going to get the characteristic of AgNO3. You're going to get a combination of NaNO3 and AgNO3, which might once again complicate your measurements. So in order to do this, people end up using conductance or conductivity water, which is of highest of purity. And back in 1894, Kohlrausch and Heydweller were able to do distillation, basically repeated distillations at low pressure, in order to reach something as low as 43 nanosiemen per centimeter as conductivity. So basically you're able to realize, as the nanosiemen indicates very, very small number, basically 10 power minus 9 Siemen, meaning that this is not going to offer any conductance by itself, meaning that the solvent water by itself will not cause any conductance. Therefore, one could reliably measure the conductivity of the electrolyte that one is using. Thankfully enough, we can actually have very simple methodology to obtain ultra pure water, which ends up having conductivity of somewhere between 50 to 60 nanosiemen per centimeter. And one of the most important considerations that we should have is that when a conductance measurement is done, the most concentrated solution of the electrolytes is used first. This is quite contradictory to other measurements that you might end up doing in a laboratory, largely because you might start with the least concentrated solution. For instance, in a measurement of absorbance, you will, using Lambert-Beer's law, you might want to start with the most dilute solution. But on the other hand, for conductance measurement, you would want to start with the most concentrated solution, because sometimes the ions end up absorbing itself on the electrode. And if you're using dilute solutions in that case, then the concentration of dilute solution is made further diluted due to the adsorption on the electrode surface, and therefore the conductance measurement is going to be underreported. So therefore, people end up generally using the most concentrated solution to start these measurements, so that any adsorption that happens ends up being taken up with the most concentrated solution. And if it's a strong electrolyte, you're going to see very soon that at the highest of concentrations, the conductance doesn't change very much for subtle differences that end up coming. On the other hand, if you're going to measure a series of solutions, as we are going to do lambda as a function of C, then you need to have a bunch of concentrations in order to measure. And there are two ways of doing it. One is by serial dilution, meaning that you take the most concentrated solution and carefully add a small portion of it to the solvent so as to dilute it serially. The advantage of this is that you're going to have very consistent dilutions, which are a little more easier to perform. But the problem that will end up coming is that if the initial solution that you're using has an error, it's going to systematically get propagated to the other solutions. On the other hand, successive dilutions is a good idea. But once again, now random errors that might come in each of the addition for different solution might result in an error. So one has to be a little careful on which approach to take in order to make these measurements. This is a picture of how an experimental setup looks. So this is the meter that ends up reading out the value of specific conductance. And the electrode that I was talking to you about a moment earlier is shown here. Unfortunately, I'm not able to get given a zoom in for something like this. If you pay close attention, the electrode here will actually be 1 centimeter apart. This is what ensures that you are able to measure everything based on equivalent conductance from this formula that you're trying to use. So if once you get specific conductivity and you know the concentration of the solution, then you know what is the equivalent conductance that you're trying to measure. So one has to be careful, because the knob that you end up seeing here is what helps you change between something like microsiemen to millisiemen per centimeter and something like Siemen per centimeter. So one has to carefully adjust this so that any values that you end up reading from this meter are reliable. Of course, to start with, the solution that you end up using has to be calibrated, meaning that people generally would use KCl solution of known concentrations, for which the conductivity or the specific conductance is known, so that they would end up calibrating the meter and the electrode in order to ensure all of the measurements that are done are reliable. So once having done that, for repeated measurements, one also has to clean the electrode very carefully and then repeat the measurements with different concentrations of solution. So therefore, one ends up getting equivalent conductance as a function of concentration. In this slide, what I have done is to summarize measurements of equivalent conductance for different electrolytes that are present. So let me go one after the other. So you have equivalent conductance measured for strong acids and strong bases, followed by salts that are composed of univalent cation and anion. And also you have measurements that are made for a bivalent cation and an anion in the example of nickel sulfate. You also have mixed example where you have barium chloride and lanthanum chloride, where barium chloride is a bivalent cation with a univalent anion. On the other hand, lanthanum chloride is a trivalent cation with a univalent anion, which is chloride. Of course, two other examples are also given where you have a salt of potassium ferrocyanide and also acetic acid. We will see why these examples are taken a little later. And what people have done here is as a function of concentration, as shown here, going from 0.0001 normal to 0.1 normal. Of course, I'm not given the units here. Basically, it's normality as we have explained earlier. One ends up measuring the equivalent conductance as a function of these concentrations at a given temperature. We will see the effect of temperature in a moment. So the moment you have this, the first thing that we had learned earlier is that lambda is going to be given by kappa times 1000 over C. So the first question we ask is that as we increase concentration, does lambda decrease? That's the first question that we have. Let's take the example of hydrochloric acid, and what you're able to realize is that yes, as you increase concentration, you are able to see a decrease in equivalent conductance. Does this follow through for all the other systems as well? If you pay close attention, you are able to see as you keep increasing the concentration, irrespective of which type of electrolyte you are using, you are seeing an overall reduction that comes up in equivalent conductance. Okay, now let's pay a little more closer attention to the various values that are present. We are looking at HCl and NaOH. The equivalent conductance at one of the lowest concentrations measured is quite high in comparison to any other measurements that are present. We will see that the Grothus type of migration of H plus and OH minus would be the reason for it later. But overall, if you're taking a look at any other electrolytes that are present, which are also univalent, anion and cation, similar to that of HCl and NaOH, the values are considerably lower. We'll not get into the discussion of why KCl is higher than AgNO3 versus NaI, but one thing that you're able to see is that depending upon the cation and the anion, the specific equivalent conductance at a given concentration is different. Similarly, you are also able to see for a mixed salt, one cannot justify why barium chloride has such a value at a given concentration, which we'll try to understand when the theory of migration of ions is being discussed. Okay, now having understood this, next thing that we would like to know is that as you change the concentration, which of these electrolytes have the most of the reduction? So let's take a look at HCl here. When you are at 0.0005 normal, you have about 422.74 units of equivalent conductance. But the moment you are actually increasing it by 10 times, which is 0.005 normal, the concentration, you're able to see it reduces by about 6 to 7 units. For all practical purpose, we can assume it's 7 units. So 7 on 422 is definitely less than about 2% reduction that ends up coming. On the other hand, if you end up taking something like KCl, same comparison is at 148 units at 0.0005 normal, but on the other hand, you're having something like 143.55 or 143.66 at 10 times more concentration. So you're having 4 units reduction on a 150, which is about 3%. So you slowly see that the change that ends up coming at higher concentration is dependent on the electrolyte in addition to the conductance, equivalent conductance that it has at lower concentration. So let's take some other example that is a little more starking. Let's take an example of sodium iodide. Here the conductance started at 125.4 units at 0.0005 normal, which is what I'm showing here. And when you ended up reducing it, you are at 121.3. So that's about a reduction of 4, and you're able to see that that's about 4%, which is more than potassium chloride. On the other hand, if you're once again paying attention for something like acetic acid, at 0.0001 normal, it's 131.6, and if you're increasing it by 10, you're able to realize it drops to about 50 units. So basically there's a reduction of 80 over 130, which is more than 50%. It's about 60% reduction that ends up coming. So what you're able to realize from this table, that each of the electrolyte behaves differently, and there is indeed a drop as a function of concentration, and the conductance that comes at a lower least of concentrations at the highest of dilutions is characteristic of the given electrolyte. And as you keep increasing the concentration, the drop that also comes up is also characteristic of the electrolyte that you're looking at. The same data is plotted here, and you are able to see the 1/C dependence for the equivalent conductance that is present. So this is for HCl, this is for NaOH, this is for KCl, the next one is for AgNO3, followed by green, which is BaCl2, then followed by, there are two things there, which is NaI in gray, if I remember right, yeah, NaI in gray, and then the black one is actually potassium ferrocyanide, and then you have nickel sulfate that is present, and finally acetic acid. So basically this is the same plot, and one point that is not being shown here is that there is a huge drop that comes for acetic acid from 0.01, I think, to that of the next measurement, which is what we were just trying to show as an example here. Yeah, and of course the drop that we are measuring here is what happens when you have 10 times change, and you're able to see, depending upon the electrolyte that you use, these are quite different from one another. And this is the same aspect that I'm trying to explain here, where you're talking about a univalent anion and a univalent cation that forms the electrolyte, and the drop, basically the conductance that comes at one of the lowest concentration of these electrolytes is quite different from one another, and the overall drop that one ends up seeing is also characteristic of the given system. On the other hand, when you're actually taking a look at KCl with respect to BaCl2 and lanthanum chloride and nickel sulfate, what ends up happening here is that this is a uni-uni electrolyte in KCl. On the other hand, you have a bi-uni electrolyte in BaCl2, and a tri-uni electrolyte in lanthanum chloride, and a bi-bi in nickel sulfate. And what you're able to see is that the drop of uni-uni to bi-bi is actually the largest, meaning that as you keep changing the concentration of the electrolyte, the drop that's seen by uni-uni is much lesser than the drop that is observed by bi-bi. Okay? On the other hand, when you're having a mixed valence salt, the drop is somewhere in between of uni-uni and bi-bi. Interestingly enough, when you have a tri-uni combination as well, it's much lesser than the bi-bi combination that is being present. So these aspects make us understand on how conductance ends up changing based on the nature of the electrolyte and the components that are composed in this electrolyte. And now this is an example that is taking it to a stark change. So once again, I'm comparing KCl to that of acetic acid. You might remember acetic acid is an organic acid, and it's not going to be completely dissociated. And the major inference that you're able to make is that the drop that you end up getting for KCl versus something like potassium ferrocyanide versus the drop that one ends up seeing for acetic acid. The drop is far much more significant for acetic acid, indicating the fact that the behavior of something like a weak electrolyte is quite different from that of the strong electrolyte, such as KCl. We'll once again be revisiting the definitions of strong and weak electrolyte as we define other parameters, but this suffices to say that the characteristics of strong and weak electrolytes are quite different in terms of the dissociation that happens between the complementary ions that are present. Remember, that could be also intermediate electrolytes that are present. We just saw an example earlier where something like barium chloride and lanthanum chloride or even nickel sulfate could be called as an intermediate electrolyte, neither strong nor weak. Okay, let me quickly summarize what we have learned. What we have learned here is that the equivalent conductance that's measured for each electrolyte is quite characteristic of the kind of ions that are present. And the example that's shown here, it depends upon the valency of the anion and the cation that are present. And the drop that ends up coming at the lowest concentration to the highest concentration is once again characteristic of the system that you're looking at. That is the electrolytic system that you're looking at. So, in order to understand things further, people wanted to know how to characterize, or rather, how to give a even more stronger definition. So, people wanted to define electrolytic conductance at infinite dilution. So, meaning that if one is able to extrapolate each of the curve such that it goes to zero concentration, that would be a term that is called equivalent conductance at infinite dilution. And how does one measure equivalent conductance at infinite dilution? There are many different equations that come, but I'm not going to be deriving each one of them. I'm just going to give you some examples. If you're able to get equivalent conductance as a function of concentration, then one could fit the curve such that it goes to serial dilution to lambda 0 with A times C power n, where A is an empirical constant and n is also an empirical constant depending upon the electrolyte that you're trying to do, while C is the concentration in normality. At the end of this lecture, I'll upload a supplementary video where we could also take a look at how, when you fit it with these equations, and one can deduce the lambda 0. So basically, one has ended up saying that an n value of 0.5 ends up working very well. Of course, we can't go into the details of why n equal to 0.5 works the best. But overall, if you're able to take lambda as a function of C and you have different points that are present and you actually fit this curve and you are able to get lambda naught, that's the way one ends up measuring equivalent conductance at infinite dilution. On the other hand, an equation, or rather a model that fits these equations better, is actually called the Onsager's equation. Once again, this will be taught to you in CHM 321, but briefly, this equation is one where you have the equivalent conductance related to the equivalent conductance at serial dilution, such that it also has other parameters that end up coming with respect to square root of the concentration. And in this case, the other empirical constants A is given by something like 82.4 divided by dt power half times eta, and B is equal to 8.2 times 10 power 5 dt power 3 by 2, where D is the dielectric constant, T is absolute temperature, and eta is the viscosity. So what you're able to see is that equivalent conductance at infinite dilution could be measured in different ways. The model that I would stick in this course would be just a simple model where the equivalent conductance changes as a function of concentration power n. And let's assume that from there, one will be able to get lambda naught. And from here on, another parameter called alpha can be defined, where it's the ratio of conductance, or rather the equivalent conductance at a given concentration of the electrolyte to that of the equivalent conductance at infinite dilution. And this ratio provides you an idea of as a function of electrolyte concentration, meaning that, remember, this is a function of concentration. So the change in conductance ratio alpha as a function of electrolyte concentration gives a measure of the corresponding fall off, meaning that as you keep diluting, lambda keeps falling off. Well, lambda naught is going to be a constant for a given electrolyte. So therefore, this gives a measure of corresponding fall off of the equivalent conductance as a function of concentration. So let's just take an example, and people have observed this conductance ratio for different electrolytes. And the example that is given here is a comparison between how the valency of the cations end up deciding how the alpha changes as a function of concentration. If you're taking a uni electrolyte, for instance, KCl, you have about 0.98 at 0.001 normal, and you increase the concentration 10 times, you go to 0.93, and you increase it further 10 times, you go to 0.83. So you have about 5% drop for the first 10 times increase, and about 10% or even 12% drop as you go from 0.93 to 0.83. On the other hand, when you have mixed valent systems that are present, which is uni-bi or bi-uni, you realize that it starts already 5% lower than the lambda naught at infinite dilution, and it's quite different. Actually, it's reduced when compared to uni by about an additional 3%. And when you increase it, the concentration by about 10 times, what ends up happening here is that unlike the previous time, which had an approximate 5% reduction, here you have much more than 5% reduction, so probably about 7% or so. And then when you have another 10 times more concentration, it reduces more than by 13% or so. So previously you had just about 0.1 unit drop on 0.93. On the other hand, here you have a 0.12 drop on 0.87, which is a much higher number. And as you keep increasing the valency of the cation, you end up having bye-bye, where you're having a reduction much lower than that of the uni. And as you keep doing serial dilution by 10 times, you're having a 0.2 over 0.85 for the first 10 times, and something like 0.25 over 0.65. And slowly you're able to see, as you increase the valency of the cation, the anion, the drop that comes up as you keep increasing concentration is significant. So the next question that comes up is that how do these measurements change as a function of temperature? And this is an example taken for KCl. And what you're able to see is that for 0.01 normal, as you keep increasing the temperature, the alpha keeps reducing. And this happens because both lambda and lambda naught keep increasing, but lambda naught increases far much more than lambda, resulting in an overall reduction in alpha. And you're also able to see this fact that comes up as that as you increase the concentration of the electrolyte, for the same electrolyte at a given temperature, there is a fall off that ends up coming, indicating the fact that lambda naught increases far much more with increasing temperature than lambda itself, resulting in a reduction that ends up coming. In addition to the change in temperature that causes difference in lambda naught, there are also measurements that were done as a function of dielectric constant. So basically what ends up coming is that as you keep increasing concentration, there is a drop in the conductivity that comes up. Let's assume it's for a given dielectric constant epsilon r, let's say of 80, which is for water. But as you keep reducing the dielectric constant, what ends up happening is that opposite phenomenon that ends up coming. So meaning that as you keep lowering the concentration, you're going to see an increase in equivalent conductance. But interestingly, when you increase it beyond a point, there appears a stage where the reversal of the effect starts to come up, meaning that you have an increase in conductance that comes up again. So basically that there is a minima that is present for such measurements that have been observed. So this was explained by Walden back in the 1920s, where the minima that happens at a certain concentration is proportional to the dielectric constant power 3. So therefore, one does not end up seeing such minima for very high dielectric constants. And as you keep reducing the dielectric constant, the phenomenon which you are getting as a V-shape starts to come. And as you start to reduce it even further, there are weird characteristics that end up coming that have been documented by Cross and Faust, as you see here. So this is an example where tetraisoamyl ammonium nitrate is kept in a mixture of dioxide water mixture, such that as you have water being 100%, you have a dielectric constant approximately 80, but as you keep reducing it to 0%, that goes to about 2.5 units. And what one is able to see is that as you keep reducing it, anomalous behavior of conductance start to come, and multiple minima start end up coming. So with this, I would like to finish off this lecture where we were able to see what is electrolytic conductance and introduce some basic terms, especially resistivity, conductivity, followed by equivalent conductance and measurement of these equivalent conductance as a function of different valencies of these electrolytes. Basic experimental considerations were also explained and the results highlighted in terms of how does these measurements change for different valency of electrolytes, followed by, or rather, valency of cation and anion present in the electrolytes, and how does it get varied as a function of temperature and dielectric constant. In the subsequent lecture, we'll be taking a look at how do migration of ions happen, an application of ionic conductance, and what are abnormal conductance that comes up, for instance, for H plus and OH minus, why do they appear differently, and how can one exploit such conductometric experiments to measure different thermodynamic parameters. As a fun exercise, the data that I've given to you, one could actually use the equation of lambda is given as lambda naught minus A times C power half, that one could use to determine what is lambda naught. I shall try to upload a supplementary video where we'll be fitting this for different electrolytes to measure what is the lambda naught that comes up from this model. Thank you very much.